In this video, we're going to take a close look at what it means for a function to be continuous and to be differentiable at a given value of x. Say x equals c. Okay, well, before we say exactly what it means to be continuous or to be differentiable, let's talk a little bit about what it looks like when the function is not continuous. So here are some graphs of functions that are not continuous. First example, let's let this be the function f, and its graph looks like this. Maybe right here we'll put in a value on the y-axis, and here we'll call this place on the x-axis, we'll call that c. And we can even give the function a value at x equals c. We can say that this is 4. Why is this the graph of a function that is not continuous? The intuition is because to draw this graph you had to pick your pen up in order to put a hole in the graph there and to show us what the value of f of c is right there. That's the intuitive idea. Using a little more mathematical notation, we can be even more exact. We can point out the following. The limit as x approaches c from the left of this function, the limit as x approaches c from the left of f of x, well, that says x is getting closer and closer to c, but from the left, the values of y for the function are getting closer and closer to 3. How about the limit as x approaches c from the right for this function? Well, as the x's here on the x-axis, as the x values get closer and closer to c from the right, the y values of the function are also getting closer and closer to 3. Together, that combined allows us to say, these facts together allow us to say that the limit as x approaches c from either direction of f of x is equal to 3. And there is no problem there. That is absolutely true. The problem is that the function actually evaluated at c is equal to 4, as is indicated by this point on the graph. And since 3 does not equal 4, this function is not continuous. That isn't the only way that a graph might not be continuous. Here is a different way. We can make a new function. Maybe we call this one g of x. Here's our x-axis. These are y values for the function g of x. Here we'll place a value c on the x-axis and consider the function whose graph looks like this. Maybe the function is coming along, doing its thing, but as it gets close to c, it suddenly shoots up to infinity, and coming from this direction, maybe it's doing something like this. And as it gets closer to c from this direction, it shoots down. This function is also not continuous. It's not continuous for many reasons. First of all, it doesn't look like f of c is defined. That alone would be a reason to say that this function is not continuous. If f of c is not defined, then the function cannot be continuous. Should we make it a more interesting example and define it at a point? How about right there? We'll say that's what f of c will be. So f of c will be this value. Should we say that's y equals 5? Okay, now why is this function not continuous? Well, we have that f of c equals 5, so that's not a problem. But here there may be a problem. The limit as x approaches c from the left of this function, as the x values get closer and closer to c from the left, the y values just keep getting bigger and bigger and go towards infinity. Meanwhile, the limit as x approaches c from the right for this function, as the x values get closer and closer to c but from the right, the y values of the function are headed towards negative infinity. Since these are not the same, we have to conclude that the limit as x approaches c from any direction does not exist. And since this limit does not exist, it certainly does not equal 5. And since these are not the same, this is not the graph of a continuous function. Great. So, that probably prepares us to show what would it look like if a function was continuous at a value of x equals c. Well, we don't want any of this to happen. Right here is x equals c again. Here are some y values. We want to make sure that the limit from both sides will be the same so that the limit itself exists, and we also want to make sure that the function is defined, and we want to make sure that all of those are coming out to the same value. So we'll put in another value on the y-axis. Here we have a graph. As x approaches c from the left, the y values are getting closer to 4. As the function, as x approaches c from the right, the y values are getting closer to 4, and f of c itself is equal to 4. So in this case, we have f of c equals 4. We have the limit as x approaches c from the left equals 4. We have the limit as x approaches c from the right of f of x equals 4. Together that means that the limit as x approaches c at all of f of x equals 4. And all of these values being the same, we can conclude that this is a function. This function is continuous. Great. Let's shift gears and talk about what does it look like for a function to be differentiable. So what about differentiability? One of the first things that we found in class is that differentiability implies continuity. That alone lets us rule out many functions so that we know that we can tell by looking at the graph that the function cannot be differentiable. For example, the following functions are not differentiable. How about this one? What is the best explanation for why this function is not differentiable at x equals c? This function is not differentiable at x equals c because it's not continuous at x equals c. As soon as you see that a function is not continuous at a value in the domain, it cannot be differentiable there. So let's concentrate on the more interesting case where it's continuous but not differentiable. Here are some examples of some graphs that are continuous but not differentiable. So here's a different function. This function will be continuous, but it won't be differentiable at x equals c. Maybe we can call this the graph of g of x. G of x is continuous at x equals c. Why is it not differentiable? The intuitive idea for the reason that this is not differentiable is that it has this sharp corner right here. That sharp corner is showing that this function is at x equals c changes too much, too fast, in order for us to define a derivative right there. Think of it like this. If you think about what's happening with these tangent lines, the tangent lines for values of x that are less than c look something like this. And then they're getting closer. As we get closer, these tangent lines are all negative. But look at the tangent lines on the other side. The tangent lines as we get closer to c from the right are all positive, so which would it be? The tangent lines are too different on either side of c in order for us to define the tangent line at x equals c. So there is no tangent line that we can draw for this graph at x equals c, and therefore we can't say what the slope of that tangent line would be, which is exactly what a derivative is supposed to tell us. Here's an intuitive way to understand what's going on. Think about what it would look like if we zoomed in on this trouble area. If we zoom in on that troublesome area, we'll get a picture that looks like this. And if we zoom in again, we'll get a picture that looks like this again. In fact, no matter how many times we zoom in, that will be what the picture looks like. So what would it look like if a function was differentiable? For a function to be differentiable. Here's the graph of a function that is differentiable at x equals c. Here at x equals c, we have no problem defining a tangent line. Right here there is a tangent line to the function. That tangent line has a slope. The slope of that tangent line is what the derivative gives us. And if we zoom in on the function right there. If we zoom in on this function, we'll get a picture that looks like this. And if we zoom in, right here is where x equals c, if we zoom in there, it will look even more so like that. In fact, the more we zoom in, the more it will look like its tangent line. So, a function is differentiable if the more you zoom in, the more it looks like its tangent line. Let's summarize. A function f is said to be continuous at x equals c if the following three conditions are true. The first being that f of c is defined the second being the limit as x approaches c for f of x exists. And finally, the limit as x approaches c for f of x must equal f of c. In fact, if you think about it, if 3 is going to work, then 1 and 2 have to be satisfied. How about for differentiability? For differentiability, if it's not continuous, then it's not differentiable. So, here is what we should keep in mind. For a continuous function, to be differentiable at c, for that to happen, the slopes of the tangent lines as we get close to C from either direction, have to be getting closer and closer to the same thing. That was really the reason why this is an example of a graph where it is differentiable at C, but here it's not. These slopes from the slopes on the left, the slopes from the left of C are not getting closer and closer to the slopes as we approach C from the right. So, for a continuous function f to be differentiable at x equals c, we want the limit as x approaches c of the derivative of f of x to be equal to, here we're approaching c from the left, we would like the limit as x approaches c from the left of the derivative of f of x to be the same as the limit as x approaches c from the right of the derivative of f of x. Okay. So we began this video asking, what does it mean for a function f to be continuous or differentiable at x equals c? And we're saying a function is said to be continuous at x equals c if we can show that f of c is defined, if the limit as x approaches c for f of x exists, and if those two things are both equal to the same value. And if a function is continuous, then we will want the limit of its derivatives from both sides to be approaching the same value.